when light or an electromagnetic wave actually hits a surface, it can exert a force on your object. And that's because of what we call the radiation pressure. The radiation pressure, same as regular pressure, it's force per area. All light exerts a pressure on different materials. It turns out, if your material completely absorbs all of the light, that radiation pressure is equal to the average intensity over the speed of light. Now, please keep in mind, this area is not necessarily the same as the area that was in the intensity equation when we said power over area. This area is the area of the object that's actually being hit by the light. So for example, if we have our lamp and we have our hand out here, the intensity, if our hand is 1 meter away from the lamp, the intensity is the 7.96 that we calculated in the last example. Power, the 100 watt light bulb over the area, the 4 pi r squared, because the light is emitted in all directions. Whereas if we were looking at the pressure, we would need just the area of our hand, because not all of the light from the light bulb would be hitting our hand. Only a portion of it would be. So that area is specifically the area being hit by the light. The difference in this equation, if the light is reflected, is a factor of 2. Now, another thing too is we're assuming the light is hitting straight on, not at an angle. So realistically, say for our hand, we're somewhere in between those two. Our hand is not a perfect absorber, our hand is not a perfect reflector. So we're somewhere in between the two. So let's find what So let's say we have our lamp. We're holding our hand 1 meter away from the light bulb. We have a 100 watt bulb again. So what would be the force on your fingertip if you held it 1 meter away from a 100 watt light bulb? Let's go ahead and assume a perfect reflector and use 1 centimeter squared as the area of your fingertip. So intensity, the average intensity, like we've just done, is power over area. So the 100 watts, this area is the area the light actually spreads over, so it's a sphere in this case. So we got, it was 7.96, right? So our average intensity, 1 meter away from our light bulb, was 7.96 watts per meter squared. So it doesn't matter if I'm to the left of the light bulb, above the light bulb, to the right. It does matter if my hand's under the base, because then the light wouldn't be getting to my hand. So if we're assuming a perfect reflector, we want that bottom equation. So the force over the area will be 2 times average intensity over the speed of light. So the force will be 2 times S average times the area over the speed of light. This area is not the same as this area. So if we had substituted in S average straight into this equation as power over area, the areas would not cancel. Just because they're both A's doesn't make them the same thing, unfortunately. So the average intensity depended upon how much area the light spread over. This one, when we're talking about the pressure, force per area, this is the area of our fingertip. We're looking at the force on our fingertip, so that needs to be the area of our fingertip. We'll want it to be in meters squared. So 1 centimeter squared, to convert, we know there's 100 centimeters per meter, but we need to square the conversion so that we have, get rid of both our centimeters. Speed of light, 3 times 10 to the 8th meters per second. Now, of course, this is going to be ridiculously small. If not, we would be getting pushed around by lights all day, which would be kind of interesting, but it doesn't happen. .3 times 10 to the negative 12 newtons. It's certainly not noticeable in any way. So, regular old lights are not generally pushing us around. We don't feel forces from them, even though technically there are forces on us, just for the fact that the waves are hitting us. But those forces are incredibly small. Now, lasers, though, are used, laser eye surgery, for example, they're used in machining shops as well to cut out different materials. And they can be used to cut out metal. So what's going to be different between our light bulb and our laser? S average is going to be different because the power will be over a much smaller area. This area would be just the little diameter, the circular area of the beam. So the intensity, average intensity of a laser is very, very large compared to a light bulb. And that's because of the area it spreads over. So the force, in turn, will be much larger. Now with laser eye surgery, for example, it's not going to take a whole lot of force to exert, what's the word I'm looking for? To alter your cornea, which is what they're doing. It doesn't take a lot of force to exert on those. But in a machine shop, if you're actually cutting out plastic or metals, something along those lines, you would need a large force to cut through it. And that is from the laser, which has a much higher average intensity than, say, a light bulb. If it had been a perfect absorber, the force would have been half as large. Yes?
Isn't that also thermal energy?
Certainly. Yeah, the laser will definitely heat it up as well. There's proposed ideas of making what they call solar sails.
Actually, Japanese tested one.
Have they?
Just like a month ago.
Cool.
It'll work.
Yeah. Cool. I don't know how fast it went, but
Right. That'll be an issue. A solar cell, big old sheet of some reflecting material, let the sunlight shine on it. Well, the sunlight has an intensity. At Earth's location, it's about 1350 watts per meter squared. Let it shine on the solar cell, which in turn will be a force. And that force can cause it to accelerate. Now, it wouldn't be very practical here on Earth because the force of drag would be significant enough to not allow the object to accelerate much. But they're looking at using it out in space. The force still isn't going to be incredibly huge, depending upon the area of that sail. But if they're out in space, outside of the atmosphere of the Earth, then there's no drag, there's nothing to retard their motion. So that force will make them accelerate, and they can travel.
well, here's one. Let's say it's a square kilometer is how big they're saying they need to go a reasonable size. And you said it was 1350 watts per meter squared. So there we go. Let's figure that out. Right here, right outside our.
Right. So the force, they want to make them perfect reflectors, so we need the 2 in there. Our area of 1 kilometer squared, we know there's 1,000, oh sorry, wrong way. 1 kilometer is 1,000 meters over the speed of light. One kilometer squared. I won't even try to figure out how they're going to make something that big.
It's one of those. It's a little way off. But I think the Japanese one was like, it was big, but it was more to test the Mylar sheet ejection system. Because like all the other ones that have happened, like, it doesn't all happen at the same time, and since it's super light, it tears.
Right.
So if you don't pull it out perfectly, it just destroys itself.
Nine newtons.
Yay!
Keep in mind, 1 newton is like an apple. So you have 9 apples
Very good.
pushing on your solar cell. But again, I mean, if there's no drag, if they're out in space and there's no drag, nothing to slow it down, it'll take a while, but it will result in an acceleration, and it will cause your object to move.
9 newtons for hundreds of years. You're going fast.
Yes, you would be going very fast. Of course, I wouldn't want to be on a spaceship for hundreds of years either.
Well, if you're going close to the speed of light, you don't.
That's true. So yes, if we had a solar cell 1 kilometer squared, which would be incredibly huge, we could have a force of 9 whole newtons.
Of course, you had 2 of them. Then you have 10 newtons.
Woohoo! And of course, another assumption though is that the light's hitting it perfectly straight on.